Hello student, in today's lecture we are going to see the definition of differentiability. Again there is one question on our mind is that if the partial derivative exists of function f of xy at point x0 y0, then why we cannot say that the given function here is differentiable at x0 y0. So if you see our previous video, you can see that there is one example. In that example we prove that the given function here, that both the partial derivative of f of x and f of y exists at 0 0, but still this function is not continuous at 0 0. That is in a single variable case. आपल्याला माहिती आहे one single y is a function, the y function असेल f of x and the given function f is differentiable at x is equal to x0, then we can say that the function f is continuous at x is equal to x0. But this is not true in our multivariable case. That's why we require a more restrictive definition. Like in a single variable function, suppose y equal to f of x, then when we say that the given function f is differentiable at x is equal to x0, if our increment delta y, that is f of x plus delta x, x0 plus delta x minus f of x0 can be written as a delta x, that is f dash x0 delta x plus epsilon 1 delta x. Then we can say that our function y equal to f of x is differentiable at x is equal to x0. For example, if you consider f of x is equal to x square and if you consider x is equal to 2, then this delta y is equal to f of 2 plus delta x minus f of 2 is equal to, what is f of 2 plus delta x? It is 2 plus delta x bracket square minus 2 square. So if you simplify this, 4 plus 4 delta x plus delta x square minus 4. This 4 will get cancelled here and this is equal to 4 delta x plus delta x into delta x. So if you observe, this is what our f dash of 2 delta x plus epsilon 1 delta x square, epsilon 1 tends to 0 as x tends to 0, and this f dash 2 is independent on delta x and delta y. So then we can say that our f is differentiable at x is equal to 2 when our increment can be expressed as f dash x0 delta x plus epsilon 1 delta x. Here you can show that you can see that the function f of x is equal to x square is differentiable at x is equal to 2 because its increment can be expressed as f dash 2 delta x plus epsilon 1 delta x, where f dash 2 is equal to 4 delta x plus this is epsilon 1 and epsilon 1 tends to 0, epsilon 1 tends to 0 as delta x tends to 0. Now same definition we are going to construct in a multivariable cases. For example, if you take a simple example, say f of x is equal to f of xy equal to x square y, f of x is equal to x square y, and we want to check whether given function f is differentiable at x0 y0, then find its increment. So what is increment? F of x0 plus delta x y0 plus delta y minus f of x0 y0. So what is f of xy? It is x square y. So f of x0 plus delta x y0 plus delta y is what? x च्या ठिकाणी आपल्याला x0 plus delta x पुट करायचा आहे, delta x bracket square y0 plus delta y minus x0 square y0. So if you simplify this, it will be x0 square plus 2 times delta x x0 plus delta x square multiply by y0 plus delta y minus x0 square y0. So if you simplify this, it will be x0 square y0 plus x0 square delta y plus, that is we multiply this x0 to this bracket. Now multiply this term to this bracket, it will be 2 times x0 y0 delta x, next 2 times x0 delta x delta y, next multiply this term to here, so you get y0 delta x square and next delta x square delta y. So if you observe this plus minus x0 square y0. So you observe this minus x0 square y0 and plus x0 square y0 will get cancelled here, and we get we can write our increment function delta f as okay. I am writing here this term first. So this 2 times x0 y0 delta x, then this term x0 square delta y plus now remaining term. This term we have taken, this term taken. Now next we can write this as 2 times x0 delta x delta y can be written as, if we take the delta x term in one bracket and delta y term in one bracket, then it is delta, if we take delta x outside, then x0 delta y plus y0 delta x into delta x plus again from this term, this 2 x0 delta x delta y can be written as 1 time x0 delta x delta y plus x0 delta x delta y, 1 x0 time delta x delta y we are taking आपण इथे घेतलाय बघा. Now next if we take the delta y outside, then it is equal to x0 delta x plus delta x square delta y, then this increment function delta f is equal to a times delta x plus b times delta y plus epsilon 1 x0 y0 delta x plus epsilon 2 delta y. So here a is equal to what? A is equal to 2 times x0 y0 and b is equal to x0 square, then epsilon 1 is equal to x0 delta x plus x0 delta y, y0 delta x plus epsilon 2 is equal to x0 delta x plus delta x square, and here you can see that this epsilon 1 tends to 0 and epsilon 2 tends to 0 as delta x delta y tends to 0. So this function f is this function is differentiable at x0 y0 because its increment function can be expressed as a delta x plus b delta y plus epsilon 1 x0 y0 delta x plus epsilon 2 x0 y0 delta y, where a and b are independent of x0 delta x and delta y. You can see here that a is equal to x0 y0, it is free from delta x delta y. Also b, which is free from delta x delta y. So if you are able to express your function as a delta x plus b delta y plus epsilon 1 delta x plus epsilon 2 delta y, then you can say that the given function here is differentiable at x0 y0. So we are going to see a definition of differentiability. So definition, let f of xy be a given function of x and y, then we can say that the function f of xy is differentiable at x0 y0 if there exists neighborhood at x0 y0 such that or any point x0 plus delta x y0 plus delta y belongs to in this neighborhood x0 plus delta x y0 plus delta y be any point in the neighborhood of x0 y0, then your increment function delta f can be expressed as can be expressed as a delta x plus b delta y plus epsilon 1 delta x plus epsilon 2 delta y. Okay, where a and b are free form, where a and b independent of delta x and delta y, and epsilon 1 tends to 0 and epsilon 2 tends to 0, as delta x delta y tends to 0 0. So if this condition hold, or if you write your increment function as a delta x plus b delta y plus epsilon 1 delta x plus epsilon 2 delta y, then we can say that the given function f is differentiable at point x0 y0. Now there is one theorem or it is called necessary condition of differentiability. So what is theorem? Suppose f of xy is a real valued function. Suppose f of xy is a real valued function defined on some neighborhood of x0 y0. Defined on some neighborhood of x0 y0. If f of xy is differentiable at x0 y0, then first f of x at x0 y0 and f of y at x0 y0 exists, and f of xy is continuous at x0 y0. f of xy is continuous at x0 y0. So what this theorem says, given function f is a real valued function defined on some neighborhood of x0 y0, and f is differentiable function at x0 y0. By using this condition, we are going to show that the first partial derivative of f with respect to x and partial derivative of f with respect to y at x0 y0 exists, and also f of xy is continuous at x0 y0. So what is given? Two things are given. First, f of xy is a real valued function at x0 y0, and f of xy is what? F of xy is differentiable at x0 y0. What is our claim? Claim first that f of x x0 y0 and f of y at x0 y0 exist. This is our claim number first. So what is given? F of xy is differentiable at x0 y0. So just we have seen the definition of differentiability. So by using that definition, since f of xy is differentiable at x0 y0, means what? We can express our increment function delta f as a delta x, that is what is increment function? Delta f is equal to, or we can write delta f is equal to a delta x plus b delta y plus epsilon 1 delta x plus epsilon 2 delta y. Okay, where epsilon 1 and epsilon 2 are the function of x and y. So, and which tends to 0, as delta x delta y tends to 0, and a and b are the independent function of delta x and delta y. So what is delta f? Delta f is what? F of x0 plus delta x, y0 plus delta y, minus f of x0 y0, which is equal to a delta x plus b delta y plus epsilon 1 delta x plus epsilon 2 delta y. So in this equation, if you put delta x is equal to 0, then what happened here? If you put delta x is equal to 0, delta y equal to 0, if you put delta y equal to 0, then this is equal to f of x0 plus delta x, y0 is equal to since delta y 0, it is equal to a delta x plus epsilon 1 delta x. Now take delta x outside from the right hand side. So if you take the delta x outside from the right hand side, it will be f of one term is missing, minus f of x0 y0, minus f of x0 y0. So if you take the delta x outside from the right hand side and divide, so left hand side we will get f of x0 plus delta x0 minus f of x0 y0 divided by delta x, which is equal to a plus epsilon 1. Now take the limit delta x tends to 0. Take limit delta x tends to 0. Then what happens? If you take the limit delta x tends to 0, then this is equal to what? This is the definition of f of partial derivative of f with respect to x at x0 y0, which is equal to a, and this epsilon 1 tends to 0 as delta x tends to 0. So what is the value of f of x0 y0, which is a? But a exists. Why a exists? Because the given function here is differentiable at x0 y0. So a exists. So a exists. What this implies? Since this implies f of x and x0 y0 exists. Similarly, if you put delta of x is equal to 0 in this equation, if you put delta x is equal to 0, then what happens here? It is f of x0 y0 plus delta y minus f of x0 y0. Then this delta x is equal to 0, so this term is 0, b delta y plus epsilon 2 delta y, and if you take delta y outside, it will be if you take delta x outside, it is equal to f of x0 plus delta x, not x0 plus delta x, it is x0 y0 plus delta y minus f of x0 y0 divided by delta y is equal to b plus epsilon 2. Now take limit delta y tends to 0. Now take the limit delta y tends to 0. What happens? This is the partial derivative of f with respect to, this is the definition of partial derivative of f with respect to y at x0 y0. So f of y at x0 y0, or this is what? Gamma f of gamma y and x0 y0, and which is equal to b. But since given function f is differentiable at x0 y0, what this implies? Our b exists. But b exists means what? F of y at x0 y0 what? Exists. So our claim number first is over. Hence here we have proved that our claim number 1. Now what is claim number 2? That the given function f is continuous at claim number 2, show that f of xy is not continuous, is continuous at x0 y0. Here we are going to show that f of xy is continuous at x0 y0. Now take the limit, since what is given, f is differentiable at x0 y0. What this implies? We can express our increment as, what is increment? x0 plus delta x y0 plus delta y minus f of x0 y0 epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1 epsilon 2 tends to 0 and delta y tends to 0, and a and b are independent of delta x and delta y. So if you take the limit delta x delta y tends to 0 0 on both sides, you will get here the limit delta x delta y tends to 0 0 of f of x0 plus delta x y0 plus delta y minus f of x0 y0 is equal to what? 0. This side on the right hand side is equal to what? 0. This term is 0, this term is 0, epsilon 1 epsilon 2 they are all equal to 0. So if you take this minus f of x0 term on right hand side, it will be limit delta x delta y tends to 0 0 of f of x0 plus delta x y0 plus delta y is equal to f of x0 y0, and therefore this is the definition of continuity, and therefore we can say that the given function here is continuous at x0 y0. So from this theorem we can conclude that if the given function f is differentiable at x0 y0 implies the both the partial derivative of f at x0 y0 exists, and given function f is continuous at x0 y0. In tomorrow's lecture we are going to apply this theorem to show that the given function f is not differentiable at x0 y0 by taking a contrapositive of this statement. What is the contrapositive of this statement? Means what? If any one of the partial derivative at x0 y0 not exist, then the given function is not differentiable at x0 y0. Or what is the again second statement? If f is not continuous at x0 y0, then we can directly say that the given function f is not differentiable at x0 y0. But in today's lecture, just we are going to apply a definition of differentiability to check whether given function f is differentiable at x0 and y0. So what is the definition to solve an example? Instead of writing delta x delta y, we are writing here delta x is equal to h and delta y is equal to k. So to check an example, in example I am writing that delta x is equal to h and delta y is equal to k. So what is our increment function? Delta x is equal to ah plus bk plus h epsilon 1 hk plus k epsilon 2 hk. So what is our original definition? Delta f is equal to a delta x plus b delta y plus epsilon 1 delta x delta y into delta x, epsilon 2 delta x delta y into delta y. Instead of that, we are writing here delta x is equal to h, delta y is equal to k, and if you are able to express your increment function as ah plus bk plus h epsilon 1 hk plus k epsilon 2 hk, then we can say that the given function here is differentiable at 0 0. Or to check only whether given function is differentiable at 0 0. This is the definition only at 0 0. So for example, let f of xy is equal to under root of xy. F of xy is equal to under root of xy. Check whether given function under root of xy is differentiable or not at 0 0. So suppose now we are going to check whether this function is differentiable or not. Suppose this function f is differentiable at 0 0, then we can express our increment function delta f is equal to ah plus bk plus h epsilon 1 hk plus k epsilon 2 hk, where a is what? Epsilon 2 hk. Already what is a? A is f of x at 0 0, b is what? f of y at 0 0. a आणि b partial derivatives बघा का ते ऑलरेडी मी पाठीमागच्या थेरममध्ये तुम्हाला प्रूव्ह करून दिले बघा. So where a is equal to f of x 0 0, which is equal to limit h tends to 0 f of h 0 minus f of 0 0 divided by h. So what is f of h 0? This is limit h tends to 0 f of h 0. F of h 0 is 0. F of 0 0 is also 0 divided by h is 0. So a is 0. A is 0. Similarly, if you find your b is equal to f of y at 0 0, which is equal to limit k tends to 0 f of 0k minus f of 0 0 divided by k. So what is b? It is equal to limit k tends to 0. Here we are taking partial derivative with respect to y. So 0k f of 0k minus f of 0 0 divided by k. But what is f of 0k? Put x is equal to 0, y is equal to k, then under root of 0k. But under root of 0k means what? It is 0. f of 0 0 is again 0 divided by k, so it is equal to what? 0. So b is also 0. A is 0, B is 0. So what is our increment function delta f? Delta f is equal to h epsilon 1 hk plus k epsilon 2 hk. Okay, that is, we can write our increment function in this form. That is, what is our increment function? F of hk minus f of 0 0. What is our increment function? F of hk minus f of 0 0. It is h epsilon 1 hk plus k epsilon 2 hk. That is, we can express our increment function in this form only, h epsilon 1 hk and k epsilon 2 hk. For okay, now what is f of 0 0? F of 0 0 is 0. So we can write this f of hk as, if given function f is differentiable, then we can write f of hk as h epsilon 1 hk plus k epsilon 2 hk. Means what? Okay. But what is f of hk? F of hk is what? Under root of hk is equal to h epsilon 1 hk plus k epsilon 2 hk. So if the given function f is differentiable at 0 0, then this under root of hk can be written as in this form for every h and k. So take a particular case for h is equal to k. Then what happens? It is h square, means what? Plus or minus h is equal to. If you take a particular case h is equal to k, then plus or minus h is equal to. Then here, if you take h is equal to k, then it is h epsilon 1 hh plus h epsilon 2 hh. Now take h outside. If you take h outside, then cancel with this h. Plus or minus 1 is equal to epsilon 1 hh plus epsilon 2 hh. Now take limit h tends to 0. Now take limit h tends to 0. What happens? If you take the limit h tends to 0, then if you take the limit h tends to 0, then on the left hand side is plus or minus 1 and on the right hand side this term will be 0. So we obtain here some contradiction. Why we obtain this contradiction? Because we assume that this function here is differentiable at 0 0. Okay, so that's why we obtain here contradiction that plus or minus 1 equal to 0, and that's why we are saying here that given function here xy is not differentiable at 0 0. So hope you understand. So in tomorrow's lecture again we are going to see some more example on differentiability, and we are going to apply that contrapositive of the given theorem to by using a simple technique. We are going to show that the given function f is not differentiable at x0, y0.